and welcome to The Complete History of Science. Series 3, Episode 5, Islamic Developments in Optics. In our previous episode on al-Haytham, we set out his theory of vision, which was one of the crowning achievements of the Islamic Golden Age. But, in answering the question of how we see, al-Haytham also profoundly changed the field of optics. In his book of optics, al-Haytham establishes several of the fundamental ideas about light, many of which are still familiar to us. For example, that light propagates in straight lines, that light travels at a very fast but finite speed, that light loses intensity as it moves away from a source, and finally, that light is transmitted by transparent media and reflected or absorbed by opaque materials. Some of these propositions, such as rectilinear or straight line propagation, were well known in ancient times, and both Euclid and Ptolemy had clearly set out this principle. But in those older works, there was always an ambiguity, because they were focused on the visual ray, which supposedly exits the eye and allows us to see. Al-Haytham, on the other hand, was clear that he was talking about light. Recognizing that light exists independently of vision meant that it could be an object worthy of study in its own right, and by extension, changed what was meant by the field of optics. Al-Haytham's study of light was also notable for its empiricism, and he set out to test propositions experimentally. His darkroom experiments, discussed in the last episode, were used to demonstrate that light travels in straight lines. In one experiment, he filled a room with dust and showed that light travelling from an aperture into the room clearly moves in a straight line. Another experiment in a clear dark room showed that light travelling through an aperture was projected in a straight line onto the opposite wall. This has led to the common claim that al-Haytham invented the camera obscura, although it's uncertain whether al-Haytham's device did actually project a clear image. Al-Haytham's interest in light also extended to the phenomena of reflection and refraction. In the Book of Optics, he describes experiments using plane mirrors, but also those with a concave or convex shape. He knew that the direction which light reflected from a curved surface could be calculated by taking the tangent line to the surface and applying the law of reflection. This led to a famous problem, sometimes called al-Haytham's billiard problem. Imagine a perfectly spherical mirror, which reflects light from some source to the eye. The problem is whether you can work out which point on the spherical mirror reflects the light from the source to the eye. He did actually solve the problem geometrically, showing that the reflection will occur at the intersection of a circle with a hyperbola. The problem, though, would go on to have a long history, as many mathematicians would try to find an exact algebraic solution. This ultimately wasn't found until 1965 by an amateur mathematician called Jack Elkin. However, al-Haytham's work in the Book of Optics was also of more fundamental importance, and he set out to verify the law of reflection. In pursuit of this, he gives a very careful description of an experiment using a semicircular block with holes drilled around its edges at regular intervals. Light was projected through these holes and reflected from a mirror placed along the diameter. The experiment demonstrates that light is only visible if it passes through the hole when it is at an equal angle about the central point. Ptolemy had already described a similar experiment to test the law of reflection, and al-Haytham was almost certainly familiar with Ptolemy's optics. Admittedly, his setup was more sophisticated than Ptolemy, and unlike Ptolemy, he was unambiguously interested in light rather than the visual ray. But al-Haytham doesn't provide us with results. This is strange, as the apparatus he employed is described in precise detail, with measurements for its construction given to the equivalent of millimeters. Undoubtedly, his setup would have been capable of verifying the law, though perhaps his desire for extreme precision is the problem. He seems to be driven by a need for mathematical exactitude, without an awareness of the necessity of allowing for a degree of experimental error. His experiments, then, arguably, were neither entirely original, nor were they quite as modern as some sources claim. However, taking this comparison with Ptolemy further, there is one significant aspect of al-Haytham's work on reflection which stands out. While Ptolemy was primarily interested in a mathematical description of reflection, al-Haytham also attempted to give a physical explanation of why certain surfaces reflect light while others don't. His suggestion was that opaque materials reflect light when they are completely smooth. In contrast, he proposes that materials which don't reflect light have pores which trap the light and stop it from bouncing back. He seems to take this analogy literally and describes reflection as being like a physical rebound, imagining light as being composed of little balls which strike a surface and bounce back at an equal angle. While this description is somewhat lacking, it demonstrates the sophistication of al-Haytham's optics, which was mathematically sound, but also receptive to the types of physical explanations typical of the philosophical tradition of optics. Al-Haytham's treatment of refraction in the Book of Optics takes a similar approach, combining a mathematical description with a physical explanation. He proposes that refractive materials allow light to propagate through them, but are partially resistant to light. The denser an object, the more it resists light, and the more it changes its speed. Again, he leans into a physical analogy, where he imagines little balls of light whose motion is being resisted. However, the important feature of al-Haytham's explanation is that this resistance to motion is not equally felt in each direction. According to him, when light enters a denser medium, it will travel faster in the direction perpendicular to the surface compared to the direction parallel to the surface, causing the light to bend towards this perpendicular line. This was a reasonable explanation, which, as it turns out, will have a long history. In the course of his work on refraction, he also described an experiment to measure refraction in between air, glass, and water. However, the experiment he describes to measure refraction is incredibly similar to the one described by Ptolemy, and he likely borrowed it from Ptolemy's optics. He also again fails to report any results, and so we might speculate about whether al-Haytham actually performed the experiment at all. One piece of evidence in favour of this is that he fails to report an important feature of refraction, which he should have noticed in his experiments. As you may be aware, when light travels from a more optically dense medium to a less optically dense medium, it can sometimes reflect rather than refract. This occurs when light hits the surface at an angle greater than the so-called critical angle. Simply put, at angles less than the critical angle, it will refract, but at angles greater than the critical angle, it will reflect. An everyday example would be looking up at the surface of a swimming pool from the bottom. If you look up at an angle, the floor is reflected in the surface of the pool. This phenomena is also well known to divers, who call the circular area of light above them Snell's window. Al-Haytham, however, failed to notice this feature, despite the fact it should have been visible if he'd conducted his experiments as described. His failure to note the critical angle, then, may suggest he never actually performed the experiment. On the other hand, al-Haytham did clearly have some familiarity with how light refracts. For example, that an increase in the angle of incidence will also cause an increase in the angle of refraction. Likewise, he was aware that as the angle of refraction increases, it does so at a diminishing rate. He attempts to use these observations to give a quantitative account and develops 5 rules for refraction. However, these rules are, despite what he seemingly believed, not generally applicable, and instead are only valid within the limited conditions of his experiment, when the media are air, water and glass, and the angle of incidence is relatively low. Given his success elsewhere, it's a little disappointing that al-Haytham didn't go further in developing a better theory of refraction. By this time, the mathematical tools to do so were certainly sophisticated enough, but, I think, he was hampered by the data available. I would speculate the most likely explanation is that his work on refraction is primarily taken from Ptolemy, with al-Haytham trying to build a theory on Ptolemy's flawed results, likely with minimal input from his own experiment. However, as it turns out, another great figure, an older contemporary of al-Haytham, had already done a lot better. Ibn Sahl is a forgotten figure in the history of science. We know almost nothing of his background, other than he was born in 940 AD and worked in the court of the Umayyad dynasty, who had wrested control of Baghdad from the Abbasids. Ibn Sahl's main interest lay in the characteristics of burning mirrors, a subject that had its root in ancient times. During the Abbasid dynasty, this area of study had been extensively explored, with al-Kindi recovering it in the works of ancient writers such as Hero of Alexandria and Archimedes. It was known that burning mirrors functioned by focusing rays to a single point, which caused objects to ignite, and there was a whole subfield of writing devoted to describing different arrangements of burning mirrors. However, in his own treatise, called simply On Burning Instruments, Ibn Sahl expands this and investigates the properties of lenses which could cause burning. He takes a plano-convex hyperbolic lens, that is one which is flat on one side and curved on the other, and uses it to focus light to a point. The effect of this is to concentrate the light rays in the same way as these mirrors. But he wasn't simply satisfied to investigate the practical effect, and was trying to show that such lenses will always cause rays to converge at the opposite side, that is, at the focal point. Ibn Sahl was successful in demonstrating this, but in the process had made an observation about the relationship between the angle of incidence and the angle of refraction. He found that, for 2 given materials, the ratio of these angles would increase as the obliquity increased. This was already known to Ptolemy, but he also found that if you applied a trigonometric function called the chord to these angles, a stronger statement was true, and the ratio of these would always be constant. This is essentially equivalent to what is now known as Snell's law, and it was not discovered in Europe until the 17th century. Unfortunately, it appears like Ibn Sahl didn't fully recognize the significance of his achievement. He in fact never highlights this rule explicitly, and his discovery was buried amongst pages of technical analysis of lenses. Ibn Sahl was practically minded, and more interested in the application of this idea, which he used to calculate the curvature of various lens shapes in order to optimally focus light. This, consequently, meant that he only had a very limited influence in the development of science in the Islamic world, and even his contemporary al-Haytham seems to have been unaware of his work. Like Ibn Nafis in medicine, it wasn't until quite late that the work of Ibn Sahl was rediscovered and recognized as part of the Islamic contribution to science. It was only thanks to the effort of the historian Roshdi Rashid, who pieced together fragments of Ibn Sahl's manuscripts, that we're now able to appreciate the significance of his work. And it's because of scholars like Rashid that we now appreciate the depth and fullness of Islamic science. Thinkers like Ibn Nafis and Ibn Sahl were aware of the work of antiquity, but also critical of it. They built upon what was there and developed theories that were both new and inspired. In a word, it was progress. We'll return next time for the final episode in this series. I hope you can join us then.